So good morning everyone. This is Dr. Hitesh Shrimali and Dr. G. Srikant Reddy. Dr. G. Srikant Reddy is overall coordinator of this course known as Applied Electronics Laboratory. This is 2 credit course and we will have different coordinators for IC161P. Those are like I'm one of the instructor. Along with that, Dr. Srikant Srinivasan is also there. This is the same professor who is teaching you IC161. That's the lecture course, so you might be interacting with him like thrice a week. And other than that, we have Dr. Rahul Shrestha, Dr. Shubhojit Roy Chaudhary, and Dr. Srinivasu B. So we 6 people are going to take care of you know uh, laboratory happening once in a week, right? And the batches are going to be rotated. So let's move forward to to the thing which we are coming for, and that's spice simulation. So I'm going to talk about spice simulation today. So that's a simulation program with integrated circuit emphasis. So if you look at the first letter of each one of them, that makes spice, and we call it spice simulation. For all circuit simulation, as the name suggests, that's actually take care of by spice simulator. So this spice simulator are many kind of spice simulators are available, like P spice is also available. One more is LTSPICE. So many variants of spice are available, but this LTSPICE is the one which is from the company called Analog Devices, and we all recommending you to use LTSPICE. And this video is explicitly for LTSPICE because that is what I downloaded. So you can see here that logo over here. You can download it from internet. So if you go and if you search about LTSPICE and download, then from the website of Analog Devices you can be able to download it. I'm not going into that, but you can do that. Once it is downloaded in your computer, there are two possibilities: either it is available for Mac OS, or it's available for Windows. So any one of them can be used. I am using Mac, so that's why it's a for Mac. But for the case of Windows, it's exactly similar. It's not so much difference. So do not worry about that. If it is Mac or Windows, both have similar hotkeys, similar way to execute it. Okay. So when you are going to start the LT Spice, you will see this window where you can start with the old file, which might be the circuit schematic, or you can start with the new blank schematic. Okay. Just for your information, whenever we are starting, and if you are seeing the circuit which looks like this one, like a resistor, capacitor, this kind of this kind of uh, pictorial representation is known as the schematic. So we call it schematic. There are many other views are also available, not only this, but if you are going for higher studies, maybe after uh, you know uh, BTech first year, second year, or in final year, you will see you need to make layout of these also. Footprint footprint Okay. Yeah, so there are many such views are available. So this is specifically for PCB, this is specifically for IC design. This is also for IC design for any power electronic circuits or even IC level circuit. Any circuit you can use it with the schematic throughout your BTech study, or maybe even going for higher studies. You will see that you are going to look at the results for schematic design, and till now you have studied only and only schematic. Do not worry about other things, but it will follow the same way. And one thing I want to start, just for starting purpose, if you are seeing 4 different kind of notations, this indicates that both the quantities are AC. Okay. V is small, I in is small, italic, it's generally for AC quantities. If both are capital, we generally give it for DC quantities. If one is small, one is capital, it is AC plus DC quantities. I believe you understand what is AC and DC quantities. DC is the one where frequency is 0 and AC is the one where frequencies are available, like A sine omega t, that's a pure AC signal. So if I want to write down this one, A sine omega t, this indicates it's AC. But if I want to write down something like this, some VDC plus A sine omega t, so this particular quantity is AC plus DC. That's why I give the notation like this. I can give this also. Both are synonym to each other. So different books are following different notation. So same things are you are going to see over here when we are going to do the circuit simulation using LTSPICE. So when you have this window for the LTSPICE, so first thing is you have to use right click. Right click is the uh, main part over here. So if you do the right click, you will see such kind of pop-up window where you need to go to draft, and in draft you need to go to components. When you go to components, there is a big list of components are available. You can see ADC, comparators, DAC, digital, filter products, many things are available, right? And note that, let's say for your example, I'm just keeping somewhere if it is available. Let's say there is amplifier. Okay, we call it operational amplifier, which name is also written over here. But amplifier is there, and various kind of amplifiers are available, like OP296, OP37, OP413. All these op amps have their own characteristic, and this is designed by different companies. Note that all the op amps, all the components you are seeing here are made by analog devices, because we are using the LT spice of analog devices. So analog devices is a big company where they are actually working on IC design of some small whatever the things you are studying in applied electronics at IC level, they are being made by analog devices. There are many other companies are in competition, like TI, or maybe ST Microelectronics, and many more. So all companies are there who are making such kind of ICs, and they are selling it also. You might know about Arduino, Raspberry Pi. Those are also ICs, and the PC board, so which are also being sold. And you can add those things also here if you want. I'm not going into that detail. You can explore that. You can add few more libraries, and note that these op amps or whatever is given here, for that you can find out through something called datasheet. So if you need to know some detail of some IC, you need to type datasheet with the name of that IC on Google. You will see how it works, what is inside that IC, and everything will be written. So in case if you are designing a project which is involving, let's say, with the OP4117, 4177 from the market, you got it, and if you want to know its characteristic, I recommend that use this op amp, and surrounding to that use some resistor, capacitor, diode, whatever circuit you are designing. You keep it here, and you will see that there will be some simulation results. That simulation results will help you or give you confidence that this circuit will behave or will work like this, and it will work. So before making the uh, exact circuit on printed circuit board or on breadboard, I recommend let's simulate it once, so that it will give you the idea. So these are the same number which are available in the market, understand, and that numbers are written on top of your IC. So if you look at the IC, which is like this, so I'm just drawing the top view. Isometric view look like this one, by the way, something like this. So if you look from this side, there will be one dot and there is semicircle. This indicates that this is pin number 1, 1 2 3 4, and thereafter 5 6 7 8. By the way, this is a standard package. So this is actually a package. Inside this package there is a circuit which is not visible to you, but it's which is covered in some sort of package. We call this black colored thing as a package. And this specific package which you are going to use most of the time in your BTech, we call it dual in line packet, or DIP. We call it dual in line package. So if you tell someone dual inline package with DIP 8, it means that it has 8 pin and it's DIP, dual inline package, and it can go from like, sorry, so there'll be like these pins can go from one layer to another layer of PCB. Or so if there is a PCB over here, you can place this and it will come out other side actually, and you need to solder it this side. This kind of uh, ICs and this kind of components are known as through hole technology. Through hole technology. But if you are seeing some other kind of PCB like a processor is there, let's say if you open your laptop, you will see that there is IC where all four side, you know very tiny pins are there, maybe 48 or 64. This kind of package will also have dot, where from where you can count down 1 2 3 4. It's going in anti-clock direction, clockwise direction to count the numbers. It might be 48 pin, it might be 64 pin. So these are also standard, and it's known as the QFN package, where all four side you have pins. But these kind of pins are not going from one layer of PCB to another layer of PCB, but it is at that point only you are soldering here itself. So when you are soldering, it's actually happening over here itself, right? So if you are doing this, such kind of devices are known as the SMD, or the surface mounting devices. So this was just a side intro. But when you are, let's assume that you are going to have this IC. If you purchase some IC from market, if it is written on top 741, if you look at this on datasheet 741, you will see that it's an operational amplifier. It's very popular one. Similar to that, 555 is also there. So whatever number is written, it indicates the number of that IC, and same number I am referring over here. So it's not like these numbers are not kept just for just for simulation purpose, but they are in reality such kind of ICs are available. So all these things you can read about it. But what we are expecting to do right now, considering what you have studied till now, you have studied the diode characteristic, and let's assume that you want to simulate this circuit. I am not going to tell you what is the name of this circuit and all, right? It's a diode, this is a resistor, and I'm giving here V in, and I'm expecting to see V out over here. Okay, so when you are doing this, understand both the quantities are AC, means having frequency component is there. When I'm drawing about this sine wave, I'm applying here sine wave, and I'm expecting some distorted or whatever the way output will be there, it will be coming over there because of this resistance and diode. Through their characteristic, you can find out its answer. Maybe at the end I'll tell you what will the answer, but before that we are going to simulate it, right? Here following things are needed when you are simulating, that what are the values of these things, right? But before going into that, when you are simulating, there are various simulation analysis are there, right? One of the analysis is, let's say, transient analysis. When you are doing the transient analysis, it means you want to plot something with respect to time. So x-axis will be always time, and y-axis will be amplitude, maybe voltage, maybe current, whatever you like, okay, or power, even charge, any amplitude will be here with respect to time. So I am not defining this value, it may be anything. By the way, just for your information, when you are going to come here, you will see that if you want to plot such kind of things, you need to use cathode ray tube, CRT, or you are going to use digital storage oscilloscope. DSO. So if you want to plot anything with respect to time, practical way, if you want to check that, then it's actually these two instruments. This is the first one is analog. We are having high tech, lab where we have all DSOs. So DSO we are going to use, right, when you are coming here. And other technique or the analysis is known as the AC analysis. Note that these two looks like synonym to each other, but that's not true. AC analysis is the one when you are interested to plot something or analyze something with respect to frequency, and maybe y axis might be some amplitude, maybe in decibel, or in volt per volt, or maybe uh, ampere per ampere, or anything. It doesn't matter. It might be ratio, it might be just volt, just ampere, just power, whatever quantity you want. With respect to frequency, if you want, then you have to follow AC analysis. But understand, in each of the cases, you need to know the start point and end point when you want to simulate. And that's true for AC analysis also. Start and stop. So you can see very easily over here, when it's a transient, you have to give the unit in seconds, and for this one it has to be in hertz. Understand, our simulator is intelligent enough. You don't need to tell that what will be the unit. You are not supposed to write down the unit of that start and stop. Just write down the numbers. Let's assume that for this case you want to simulate it from 0 to 1 microsecond. So in that case, when you are going to open the simulator form, where you are going to write down start 0 and stop 1 u. U is micro over here, right? Nano is nano. Other are not creating much problem, but u and micro are same, by the way, right? So you don't have to write down seconds. And similarly here, if you are doing for this AC analysis, this start is referring as 0 hertz and stop is referring as 1 microhertz, right? So always remember, this is what I experienced previously. Most of the time people or all students are asking me, sir, my simulation is not working, because they are adding extra units over here, which is not required. Simulator is intelligent enough. Just avoid them. Okay, don't use them. Okay, units don't use, means volts, hertz, seconds, amperes, don't use that. And third technique is actually DC, where you want to check the DC, let's say, characteristic. Okay, so it's a single point analysis, where voltage you are applying, and the what is the different voltage, current, all these things at zero frequency. But note that this also having many synonyms words are there. Maybe after few classes you will learn that you are also doing you know biasing analysis or bias analysis. Okay, some people also call it DC bias analysis, right? DC bias analysis, right? And other thing is q point analysis. This is quiescent point, right? All are mostly synonyms to each other. Okay, so they are coming under uh, same analysis category. Some simulators are giving something in explicitly different names, but they are having some extra features, that's why they are giving. So you need to find out what are those extra features, right? So that you need to check, right? So these are the different kinds of analysis. Let's start with the simulator. So I'm again repeating, I'm going back. When you open the LTSPICE, it will look like this. Right click is the only one which is going to help you everywhere. So wherever you stuck, keep the right click. You will see such kind of things will be there, where you need to go to draft, where all the components are available. Add components. I want to make that resistor and diode based circuit. I am going to write down resistor. You can see there are two resistors are available, right? Any one of them you can take it. It's depending on the value what you are taking, right? If you want few more like potentiometer and other things, those are also available here in this library. You can find it out, given at the, you can see this uh, top directory is there where all the path and everything is given, right? So if you choose this, there is control R. Control R is the one, R for rotate. So when you do the control R, it will be rotated. So whichever direction you want, as many time you rotate it, it will be rotated. Just keep it there, right? And escape will be escaped. Now again I want to add diode. I'll go to draft, I'll add component. I'm going to write down diode. I should have somewhere diode, right? Take that diode. If you want to change the orientation, it's okay. In this case it's not required, so I am not changing the orientation for this one, and I'm keeping it. Now I want to connect, next thing is the wire. So if you are using very frequently, then you will remember all the hotkeys. If you want to see which are those hotkeys, those are written over here. So F3 is for wires, F2 is for components, right? After few days you will remember it, and maybe if you're doing uh, like again and again, there is no problem. But let's assume that you want to find out and you don't remember the hotkey, which is F3, then wire is coming from draft. Take it and just connect to one point to another point. So this is connected, and escape will be uh, will help you to escape the window, right? Now other side is connected to ground terminal. You might be knowing ground is 0 volt, right? So just go to that net wherever you want to add ground. Keep the right click here and give the label net. Label net will have following possibility: either you like give ground, common, both are almost similar, but we are going to give absolutely 0 volt ground, and that is what we are going to keep it here. So now this is connected to ground. If you want to drag something, you can go to edit and drag, delete, whatever you want to do, you can do it. I'm dragging it, let's say, for here. Now the next thing which is required for our case is the input. So again, you want to add input. So input is also available from only one special key, which is right click. When you do the right click, go to draft, go to component, because it's also component. In that you are going to add voltage source. So you can add this voltage, keep it here. Next thing will be wire. So you go to draft, wire. You can speak.
Okay, so there is a question. Question is that how do we know whether the source which we are putting, is it an AC source or a DC source, based on these values written there or based on the symbols?
You're asking me, or huh? Okay, so that's the next thing, as rightly pointed out by Professor Gopi, that this thing which have been added, it's a DC source. You can understand this. It's a plus and minus, right? It's a standard way of keeping DC. So we need to change that now. So you have to go to that one. You can see there is one pointing finger is coming. Go to there again. Use right click, and if you want to give some DC value, because this is a DC source, then it's fine. But if you want to change it to something else, go to advanced, where various kinds of sources are available. You can see DC, pulse, sine, exponential, SSFM, PWL, PWL files, all these things are given, right? So it's up to you which one you want to use. For considering the BTech first semester, second semester course, I would go till just DC, pulse, and sine. Okay, because rest of the things maybe you can learn it in advanced courses. Maybe when you are going for communication, or maybe analog circuit design, or other courses, right? So first one was DC. I believe you understand what is DC. So this is a DC source. Let's say its name is V in, both are capital, right? So it's DC. DC requires only one thing. What is the value of this DC value? Again, I'm telling you, if it is a voltage source, you don't have to write down its volt. If it is 1 volt, just write down as 1, right? If it is 100 millivolt, write down 100 milli only. So our simulator is intelligent enough, right? So this is only thing is required. DC is providing DC. But if it is like this, right, then this is an AC source or sine source. As this one is going to be plotted with respect to time, this is also going to use transient analysis, as we have already discussed, and it requires following things. It's a sine omega t, right? So it requires the amplitude, the frequency in hertz, not in radian per second. It requires in hertz for our our simulator. It understands in hertz, but if you want to change it to radian per second, of course you need to use some advanced you know advanced settings of the simulator, but I don't recommend to do that. Please keep it in hertz so that we can help you uh, uniformly. But if you are changing to radian per second, just let us know, or let your TA know, so that he will help you accordingly. Okay, so I'm considering that it's hertz only, so we need following things. I need amplitude. Understand, this amplitude is the one which is this one. Understand, when I'm saying a sine omega t, this is the a, so actually it becomes double, right? It goes to minus also, right? So that is what you are going to see. So it's a sine omega t, that's the amplitude. But other than that, sometimes it will happen that you are interested in giving not only like this, but something like this. Or I'll change the symbol. You might be interested in like this, where DC plus AC is there. So that requires one extra term. In simulator, we are going to call it offset. Some simulator call it explicitly DC offset. So DC offset, whichever DC offset you want. Let's assume that I am having one example of V in is equal to 1 plus 0.5 sine 2 pi 1 mega t, right? So in simulator, you will follow these numbers. DC offset is 1. Again, as I recommended, do not add anywhere unit. Amplitude, it's 0.5. Then frequency, sometimes some simulator will ask both the things, like frequency as well as period, or any one of them. So please give any one value, because sometimes if these two won't match, then your simulator will tell you that it's not running the simulation. Your simulation will be stopped. It will give you some error. So my recommendation is choose any one. Either you give 1 microsecond or you give 1 megahertz. Okay, so I generally like to give just frequency. It's up to you. Whatever you like, you can give it, right? And maybe the number of cycles. After how many cycles this signal has to be stopped. But we don't want to do that. Do not give anything there. Okay, do not give anything here. So this is for the sine source, if source is sine. But if source is pulse, this is very important a source when you are working with digital. When digital circuits are there, you might aware of the fact that in digital you need logic 0, logic 1. Here in simulator, we will refer this one as V0 and V1, or maybe V1, V2, depending on different simulators. Name might be different, right? So first one is always logic 0 and second one is logic 1. Second one is the frequency, or might be period. Sometimes it's also required delay. Here also I forgot to keep delay is also required. You can add some extra delay if you want to add delay. So if it is starting from here, amplitude with respect to time, then there is some delay and thereafter the signal will start. Same thing you can do it over here also. If you want to give some delay, you add the delay. You can add v0 v1, that's logic 0 and logic 1, frequency and period. Other things are also there. If you don't give it, there is no problem. Those things are rise time, fall time. Sometimes some advanced simulator will add jitter also. Okay, so rise time and fall time are referring to the signal. You might think that square wave look like this one, but in reality it is not the fact. You will see something like this. So you need to define what is the rise time, fall time. If you are not gone through these terms, then I recommend that it was part of IC 160. Please go through it, or it's available it's very simple terms. So please go through it. It's a time going from 0 to 90%, and another one is in a reverse way, fall time. So generally, if you don't give that TR and TF, which referring to rise time and fall time, if you keep it, you know, empty, and if you don't add anything, it will automatically take, you know, something like 10% of period. Some simulator are taking, 5%, 1%. All simulator has different things, and some simulator like LTSPICE is going to take 0%. So it's there is no rise time and fall time. Okay, it's as good as ideal, but in reality that's not true. Reality has this kind of square wave, right? So you should add a rise time and fall time, but for starting point, until you have not studied digital electronics or anything on digital side, I'd recommend keep these entries empty. It will be automatically taken care by the simulator. So that is what I was telling. So in this case, DC value, you know that you need to add only DC value, which is only 1. If it is pulse, you need, as I told you, V1 and V2 are the terms are there. So you have to write down on voltage and initial voltage as 0, or maybe sometimes it's different also. You can give it in minus. So it's depending on that. T delay, rise time, fall time, T on second, for how much time you want to have the on period to be on, and T period. Understand, this is very interesting because you might have this kind of signal, and you might have this kind of signal. Understand, and let's assume that I'm not so much accurate in a way, but this period and this period is exactly identical, and let's assume that this is also same, like this is T, everywhere it's T. So its period is T, both side is T, but these on time and off time are different, T on and T off. If both are same, we are going to call it square wave. If T on equal to T off, you are going to call it rectangular wave. If T on is not equal to T off, like the case here, it's not compulsory that T on has to be smaller. It might be other way around also, that T on is on for more time and T off is lesser time on. So this was the thing. Other than that, there is one more wave, impulse. Impulse is the one where just one, one time it's getting on and then for infinite time off, or it's a reverse also. Okay, so various notations are there. So if you don't give the time period in your simulator, if you don't give T on period or T period, it will be like not repeating that signal ever, and it will be impulse. If you are giving T on time and T period, such that T on is half, it will become automatically square wave. If you are giving T on is smaller, it will become rectangular, or giving T on is more than T period by 2, it becomes rectangular, right? So similar to that, there are some cycles and other things are given. So all these entries are referring to that. Any entry left?
So I have a question
Hmm.
here. So this T on T off, so the unit is by default
Seconds.
seconds.
All are seconds.
Okay.
This is time. Time delay is second. Time T rise is second. T fall is second. T on is second. T period is second. Here there is no option of having frequency.
Hmm.
Frequency of the signal.
Okay.
But some simulator are giving frequency also.
Okay.
So depend, if you are using PSpice, it is there.
Okay.
Okay, in LTSPICE it's not there, but as I recommended, choose only one. If you are choosing T period, and like T period and frequency has to be having the same relation, otherwise it will give a simulation error.
Okay.
Okay, so don't give two at a time.
Okay.
So this was pulse, and again like sine, which has, you understand what is DC offset, amplitude, frequency, T delay, and other things. Like this is for phase, right? So again, like uh, do not give theta and phase together, right? They have relation, right? So I recommend, if you need it, then and then use only one. Theta and phi are, the numbers which you already know, right? This same thing. Phase is phase difference, right? So phi, uh, actual equation is a sine omega t plus phi, right? So you assume that phi is 0, but in reality, you might have some other value also. So if you want to add that, you can add it here. So these three things I'm explaining now. Other things you can explore it, maybe you can understand by plotting it also. So I recommend, if you want to learn it, rather than going into Google search, go to that particular thing, choose that source, and plot it. After simulation you will understand what is happening. Go with some different, like tau value is given, fall delay, rise tau, all these things are given. Feed that and try to understand how they are working, right? And similar to that, others are also available, right? So I'm not talking about that, but if you are interested, you can. Okay, I need to feed value because we are running transient analysis, or with respect to time. Let's assume that this is 0. Amplitude I am giving, let's say 1.1 volt. Frequency 1 micro. I am not feeding any other thing. Okay, oh sorry, frequency has to be 1 mega, right? It's in hertz. So after 1 microseconds of period, this will be repeated. This is the thing. So now it is, you can see here, sine 0, 0 is DC offset, 1.1 is amplitude, and this is the frequency, right? Okay, so this is all done, no problem. If you like to give, let's say, some of the name, like some advanced people, they are label the nets with the name. Let's say if you want to give it V in, let's give V in, no problem. If you want to call this one as V out, you can call V out also. Otherwise some random name will be coming, like NE 121 123. You will not be able to understand where are those. So I request that you should give some name which you can identify. Once this is done, look, uh, if we are going to simulate, this will not get simulate. Understand, this is a run symbol. One guy is running, so it's for run. If you run it, it will not run the simulation, because my simulator does not know that which analysis I need to run, like transient, AC, DC, or whichever you want to have. So that we need to give. If you need to add that simulation analysis, again, only right click is required. Go there, and you have to give spice directive. In spice directive, there is a space is given. So if you are expert enough, and if you know directly by, you can write down also. This is spice also is a script, or it has some sort of net listing. We call it net list, we don't call it script, but it's a kind of script. So it's simulating that given script, not this GUI. So uh, maybe later on you will learn it how to write down direct thing. I know it, but If you do not know and you are writing first time, again use the right click, which is the only thing available to us. Go there and ask him to help me to edit, and go there and find out the analysis command. So it will write down the command for you for different analysis. You might be interested in transient, which is with respect to time in a circuit which has been kept over here. I have given input with respect to time, so I would like to give transient. If I have given frequency as an input, I would have given frequency AC analysis. If it is DC sweep, which is very much required in a case when you want to have IV characteristic, and for noise analysis, if you want to observe the noise will be there. This is another uh, advanced characteristic. And as I told you, if you just want to check the DC bias point, right, or Q point, you can do it from here. So for considering the example which I am taking, it requires only transient. Other things you can think about it. As I told you, for transient, it's important that you have to give what is the stop time. Considering the fact that we are giving 1 megahertz of frequency, if I want to see 10 cycles, I need around 10 micro. If I keep the end time as 10 micro, so again I'm telling you, do not add seconds as, okay, it will give you an error, right? So stop time is 10 micro, means you are starting from 0 seconds to 10 micro, and in 10 micro you will see 10 cycles. Now time to start and saving data and all other things which is not required. Okay, these are the advanced thing. If you want, you can do that. What is the time step and all these things, you want to take control of that, because although it looks continuous in time, and simulation also looks continuous in time, but this computer at the back end, it does the simulation at fixed interval, right? So you can control that. Those things I am not going into detail right now. Maybe when you will be here in campus, when you become expert of this fundamental thing, then we can discuss about it, right? So let's go with this. That command is very simple. If I want to run transient analysis till 10 micro, the command is just minus dot tran 10 micro. If I want to run AC analysis till 1 mega, it's dot AC 1 mega, right? So such commands, if you don't remember or if you don't know, always use right click and take the help from analysis command, right? And you can add that. Once this is done, you can make it okay. That this analysis, you can keep it wherever you like. So I kept it here. So it's transient analysis 10 micro. In addition to this, if you want to run DC also, you can run multiple analysis together also. So I'm not doing this, but you can add few more things, DC also, noise, everything, you can do it one by one. Now we look like ready, but it's not true, because still resistance value we have not given. Let's assume that I am keeping the resistance value as 1 kilo ohm. Understand, again I am not going to add the capital omega at the end, because it is automatically understood by the simulator, or I am not going to write down OHM. Don't do that, it will give you error. So you can see here the resistance with 1 kilo, and diode is a standard diode, ideal diode with the. So you must be knowing that there are two kinds of diode. One is PN junction and ideal diode. One is ideal and one is PN junction. Ideal is the one which you are studying in book. Of course, PN junction is also you are studying in book, but ideal is the one where we are following two things. This side is V anode and other side is V cathode. So if V anode is higher than cathode, then it's forward bias. If V anode is greater than cathode, and if it is not, then it's open. This is what we have learned in school, right? This is ideal, but in reality it's a PN junction. So V anode has to be 0.7 times higher than cathode, otherwise this won't work, right? And similarly for reverse equation also you can write down. So this is forward bias and reverse bias. Very quickly I'll just review the circuit, although this is not meant for teaching circuit. So if I am giving here like this, and if I'm applying 1.1 volt of, so this is 1.1 and this side is also minus 1.1, frequency is 1 micro, right? This is what we have done, right? So if I increase V in from 0 to 0.7, understand, till that time this is not going to be on, because if it is zero point 0.1 and this is 0, still this side is not zero point 0.7 addition to that, right? It has to be higher than V anode plus zero point 0.7. So it is 0, but this is not on, so this is off. During this time when this is off, I am holding a multimeter over here. Multimeter is the one which is going to give me the voltage value, right? So when I am holding it, the input impedances of the multimeter is R mult is equal to infinity or very high, and this R I kept it 1 kilo. This is around 1 mega, by the way. So at this multimeter point, what I am going to see, it's going to be equal to R mult divided by R mult plus, that's 1 kilo. R mult is replaced by 1 mega, 1 mega, right? So it's times V in, right? So 1 kilo is very low, so you can cancel both of them. So output side you have V in only, with some small negligible error. That error is coming because of, like, it's in very small number will be coming, right? We are not going into detail of that, but if this is the case, when it becomes open circuit, do not forget that there is one more circuit is there, which is multimeter, whose impedance is 1 mega, offered by this multimeter. So whenever you are saying this open, its V in is transferred over here, right? So this is the case. So let's start. If it is 0.1, it's transferred, no problem till that point. If I give 0.2, same thing is happening, this is becoming open circuit. Something will happen when zero point 0.7 volt is coming, and at that time this becomes ground. When it's ground, circuit find out the least resistance path. So because of least resistance path, it's connected to 0 volt only. This side is 0 volt. It doesn't matter what you are connecting here, right? So this circuit will make the short circuit to 0 volt, and it will be the value which was there. So after zero point 0.7, it is remaining at the same potential where it was, and later on when you go down to zero point 0.7, again this becomes open. When it's open, it's going to follow the input. So this is what we are expecting. Understand this, these are the sharp things are happening, but that's the wrong thing. When you are going to simulate, you will see that it's little bit, curves are you are going to observe, right? So that we are expecting. I believe you understood it. If you don't understand, like my TAs or me or maybe other professors can help you later on when you are doing this experiment, right? So if I want to simulate it, you have to use run symbol, which is kept over here, and you will see some window. Now the thing is, what you want to simulate, that we need to tell him. So if you go to, let's say, V in, you will see that red color, some probe is coming. If you click that, you will have V in over here, and if you click here in this one, when you are giving the amplitude and all, like we can give 1, and frequency wise you can give something like, let's say this is 1 megahertz, and DC offset I gave it 0. So then if I run it till 10 micro only, if you run it, I'm going to see such kind of thing, and you can pointing out with the multimeter. You will see this is the input signal, which is exactly what we were expecting. It's starting from 0, and frequency of that one is around 1 megahertz. So this is visible thing. Now you want to have V out. So on top of that one, you can plot V out. You can see here almost after zero point 0.6, this is actually getting, you know, almost clipping off, right? So this is giving the output as expected. Similar things you can do it, and you can simulate it, and you can check the output as we have shown over here. And you can have all the possibilities, like in sine wave also you can see that here the requirement of frequency is not like if you're writing mega in capital, it was creating a problem. However, you can give some engineering scientific numbers also, like 1e6, then also it will simulate it, and it will give you the required simulation, right, like this and as follows. You can see it gives the expected output. But understand one thing over here, that this circuit and all the simulations are happening not only with this graphical view. At the back end, this understands some sort of mathematical equations or circuit equations, like V equal to IR. Diode will have its own equation. So all the models are available with the simulator. That's how it's happening. And it's not simulating this circuit, it's simulating some sort of netlist. We call the netlist, if you remember, at middle of our lecture we talked about spice script. It's not spice script, but we call it spice netlist. And how does it look like? If you look at that, you can see over here, if you can compare this graphical part and this netlist, you can see here, I can see there are three different components are there, whose names are R1, D1 and V1. And R1 is defined between two ports, V in and V out, and whose value is 1k. So same thing is written, R1, V in, V out and 1k. That's the meaning of the netlist. D1 is between V out and 0. Look at this, this is 0 and its name is D, right? Similar to that, there is one voltage source whose name is V1, which is between V in and 0, and that is defined by sine, whose DC offset is 0, amplitude is 1, frequency is 1 mega, and 0, it's a 0 delay. Now the only thing is, here you can see there is some sort of you know variable is that D, and that's the model is the one which is defined here in a given library with a given path. What exactly this model does is, the equation wise, every diode might be different in terms of maybe sometimes current, sometimes voltage. You might have studied a 0.7 volt as a cut-in voltage, but in this diode it's nearly around 0.65. It's that's the cut-in voltage. So those things are written at the back end in this library or the given library path, as I have explained you for op amp and other things, whose mathematical things are written in library path, and the path is defined over here, and whose models are here. Like the case of R1, the model wise what should be behind resistor is, it is model with V equal to IR. Understand? So if I want to find out current, that's V in minus V out divided by R1. That's the current, and that's the model. We call that one as a model, but it's a circuit model. So that is written over here, and some of the standard components are defined as per our equation given in the book. However, some of the models are not defined, like in this case of diode, op amp, many other things like comparator or many other circuit elements whose models are not directly given by the standard way. It is given by the company. Then those models will be defined at the given library. and that is what there. And the last one is which simulation you want to run, dot tran 0 to 10 micro, and this is going to be n. So this is what the actually simulated at the back end, not this circuit. This is a graphical way, but in reality, the simulator takes care of these things. So whenever you make the circuit, it creates circuit simulator, and through circuit simulator, it find out the netlist, and through netlist, it find out the required voltage, current, and all these things from there. So that is the thing, and that's all from my side, right? So thank you very much.